Good morning, welcome back. Happy Friday. Today's the 17th. Today is our 24th lesson. We are talking about the quadratic formula again. This is our second day on the quadratic formula, and we will introduce a brand new set of numbers called the complex numbers. Coming up on Monday is a new set of problems. They're all about word problems. That Monday material is not on the quest, which is coming up Wednesday. Okay, so our fourth quest is Wednesday. It is on 19 through 24. Today is 24. Okay. Any questions on the calendar? Okay. One quick announcement that has nothing to do with our particular class, but coming up on December 5th here at GCC, there it is. There is a free resume writing workshop. That's a Tuesday, 12 to 1:30. It looks good. It's free, but you do have to pre-register. Some outside group is coming onto GCC's campus to help our students write or update their resumes. So the URL for this page is kind of long, so I have made a tiny URL right here. Write it down or take a photo of it. This will direct you right to this page. Any questions on that? Okay. All right, and then let's see here. One other thing I want to say. Yeah, one other thing I want to say about the quiz, which is coming up. So we have 3 different methods that we can use to solve quadratic equations. For example, if I gave you something like x squared equals 10, what would you do to both sides to solve for x? You'd take a square root, and you just get x equals square root of 10, but don't forget to put in what? Plus or minus, right? Every quadratic equation has 2 solutions. So that is the method that we call the square root method or the rooting method. Another option would be to take something like this and try to factor. And factoring this one involves our 2 by 2 box, yes? Okay, and so if you do, say dot, 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 you're doing the box, eventually you will get x minus 4 times x plus 3. And then you set each of these pieces equal to 0, and you get your 2 answers, right? So that is the factoring method. Completely separate method to solve quadratic equation. Or, last class, we saw the quadratic formula, which will solve any quadratic equation, and it's our fancy formula with a's and b's and c's, and you do x equals negative b plus or minus a whole lot of stuff divided by some other stuff, right? And when you plug all of those things in, eventually you will get the same answers that we got before, 4 and negative 3 in this case, okay? 3 completely different methods to solve quadratic equations. How do you know which one to use? Well, in the first case, if there is no x term, right, it's only 2 things there, x squared and 10. There's no term with just plain x. It is the rooting method all day, every day. If it's got all 3 terms, then you can try to factor. Some of the times it will work, but some of the times it will not be factorable. So if it's factorable, that's probably the easiest thing to do. But if it's not factorable, then the quadratic formula will solve every single quadratic equation. But the fact is, if you can use the quadratic formula to solve every quadratic equation, why do we have to ever use those other 2 factoring methods? Well, because they're easier than the quadratic formula in the problems that they apply to. And so on the coming quest, here's what you are going to expect to see. There's going to be one problem which says solve this quadratic equation using the quadratic formula. It will be very clear in the directions, and I'll even give you the formula right there on the page. But then you're going to see a whole other page of problems with quadratic equations, and it's going to say do not use the quadratic formula at all on this page. And that is my way of forcing you to make sure that you know how to do the factoring method and to make sure that you know how to do the rooting method, okay? I'm trying to be really transparent here. You got to learn all 3, even though technically, if all you knew was the quadratic formula, you could solve any quadratic equation I throw your way. But I'm going to give you directions to prevent you from doing that. Any questions on that? Okay. So let's jump in here. Quadratic formula day 2. In this lesson, we see how we can use part of the quadratic formula to determine something called the nature of the roots of a quadratic equation. We'll define that soon, nature. And we discover a brand new set of numbers called the complex numbers. So here we go. Here is graph D. We've seen it before. And the equation for that particular parabola is y equals x squared minus 4x plus 5. So I'm going to redraw one of my grid lines here. Suppose that I asked you how many x-intercepts this parabola has. How many does it have? None, right? Doesn't have any. This thing never hits the x-axis, am I right? You guys probably have a better looking picture on your page than on my screen. So there are no x-intercepts, but suppose we didn't know that. Maybe we don't have the picture in front of us. In order to find the x-intercepts, which variable are we letting equal 0? X or y? It's the y, right? So to find the x-intercepts, we let the y equal 0. It's always the other variable equal 0. And so if you tried to solve this equation using the box method, you would discover that this does not factor. It is not factorable. Our fancy word was irreducible. But you could certainly use what magic formula to solve that equation? The quadratic formula, because as we said, you can use the quadratic formula to solve any quadratic equation under the sun. Well, look, the quadratic equation is going to give us some answers. It's going to give us 2 answers. But what does that even mean? Like, we're looking for x-intercepts. We know that there aren't any, but the quadratic formula is still going to give us 2 numbers because that's always what it gives us. So, like, where is this thing going to break down? Like, the quadratic formula isn't going to say, hey, stop, this didn't work, there are no x-intercepts. It's going to give us 2 numbers. And I want to know what 2 numbers are we going to get, given that there aren't any x-intercepts. So let's give this a shot. Okay, so let's go ahead and fill in here. I've got, like, the shell. Let's put A's, B's, and C's real quick. Pop quiz that doesn't count for anything. See if you can fill in A's, B's, and C's. No numbers. Just how much of that quadratic formula do you have memorized? Okay, once you've got your best attempt written down, you can check your work against mine. Negative b plus or minus square root b squared minus 4ac, all divided by 2a. Again, you don't need to memorize it, but a little bit of practice, it's not too hard. Let's write down the values of a, b, and c. A is the number touching x squared. What is it? 1. It's invisible in this case. B is the number touching x. Negative 4. C is the number not touching any x's. 5. Okay, so those are our values of a, b, and c. We're going to carefully plug them in to our quadratic formula. Negative b, that is negative, what number? Negative 4. It's going to become positive 4, but let's not skip any steps. Plus or minus square root of b squared. What am I putting? Negative 4 squared. That's what Rachel said. This is what Rachel meant. Negative 4 squared. Just right. We need parentheses. Negative 4 squared, that is negative 16. That is not the right answer. Even if you type it in your calculator, you're going to get negative 16, which is not the right answer. Parentheses every time. Okay, minus 4 times a, that's a 1. C, that's a 5. Lots of parentheses there. Divided by 2 times a, that's again a 1. Okay, parentheses for every a, b, c, every time. Equals, so now we'll do a little arithmetic. Negative negative 4, we said that's positive 4. Plus or minus square root of. Negative 4 squared, how much is that? 16. Ultimately, is this going to be a minus or a plus? That is a minus. There is a single negative sign there. So I copy it. 4 times 1 times 5, that's easy. That's 20. Divided by 2 times 1, also easy. That's 2. Okay, last step here. 4 plus or minus square root of 16 minus 20, that is negative 4. Divided by 2. Okay, and then we pause, and we look at that square root of negative 4, and we say, uh-oh, because up until this moment in the semester, square root of negative 4, we would stop and say this is not a real number, right? That would be the end of the problem. Okay, but it turns out that mathematicians have given meaning to the square root of negative numbers. We haven't seen it before in this semester, but we're going to see it right now. And some of you might have seen it already in a previous math class. Do you know what magic letter we're about to introduce? I, yeah. So I is the heart of the imaginary numbers. I for imaginary. So unfortunately, this set of numbers here has the name imaginary, and it's unfortunate because it means that a lot of folks think that they are somehow less legitimate as numbers than all of the real numbers we've been talking about this semester. Well, this is just like a historical consequence. The real numbers were defined. They were called the real numbers for thousands of years, and then somebody said, hey, wait a minute, I got this other set of numbers that doesn't count. It's not one of these things that you've been calling the real numbers. So what are we going to call it if it's not a real number? Okay, imaginary is where it came from. But these are legitimate numbers that we're talking about. Square root of negative 4 is just as good as 256. Perfectly valid number. Okay, turns out that these numbers are called complex numbers, and they're used in many fields like engineering and in medicine and other places as well. So we're going to start not with the square root of negative 4, but instead with the square root of negative 1. We'll come back to that negative 4. The question of how to define that square root of negative 1 arose when 16th century Italian mathematicians tried to solve cubic equations, things where the highest power was a 3. And it turned out in solving those cubic equations, finding the value of x that makes this true, they came upon these really fancy, funny square roots of negatives. And so what they were studying led to this definition. We denote the positive square root of negative 1 with the letter I. That is, we let I equal the square root of negative 1. Any place we see the square root of negative 1, we immediately replace it with the letter I. It is not at all unusual for mathematicians to define a special number to be a letter. What's the most famous number that you know that is known by a letter? It is known by a Greek letter. Pi, right? How much is pi, roughly? 3.14, right? And change. But we can't write it all out because it goes forever and there's no patterns. And so we just say, hey, we're going to use this letter, pi, the Greek letter for p, to denote this famous number that has to do with circles, right? So here's another famous number. It's the square root of negative 1. We are going to denote it with another letter, not pi, but in this case, I. So here's how we handle it. Let's suppose that we have the square root of negative 4, which is the one that we're playing with. Okay, we are going to write this as negative 1 times 4, right? And then we're going to use our fancy product rule for radicals. So do you buy that I can take that one radical and split it up into two radicals like that? We've seen that property many times. And then we say, hey, square root of negative 1 is our new favorite number. What are we calling it? I. So we just change that to an I. Square root of 4 happens to be a nice number. It is 2. So I times 2 is the answer to the square root of negative 4 that we were interested in. Okay, how do you handle it if it's a number that isn't a perfect square, like negative 15? We do the same thing. You're looking over there. Don't look. That's the answers. Look over there. Square root of negative 1 times 15, right? Still negative 15. And then we use our famous product rule here to write two radicals. And then that square root of negative 1 becomes I. And the square root of 15, we can't do anything with that, so it just stays. And that's it. I square root of 15 is our answer. And we'll do one last one. Square root of negative 12. That's a negative 1 times 12, split into two radicals. Negative 1 becomes I. Square root of 12. Okay, you could just write square root of 12, but actually the square root of 12 I've given you before, and you have simplified it for me. And so we still need to simplify it, even though this fancy I is popping out. 12, we're going to rewrite as what times what? 4 times 3, right? Not 6 times 2, but 4, because 4 is a perfect square. Okay, and then square root of 4 comes outside and becomes 2. And then there's an I also outside, and then there's a square root of 3 inside. So 2 times I times the square root of 3. That's our simplified version of the square root of negative 12. Just a convention, if there is a number that pops out, you typically write it in front of the I, but a radical typically gets written after the I. It's not wrong to reverse the order. You can change the order however you want here, but that's the typical order in which we write it. Okay, so I actually don't need to see you do the splitting and the -1 times and all that jazz. Let's just look at the shortcut here. Square root of -15 turned out to be I times the square root of 15. So what's our shortcut? You just make the number positive and you put an I in the front of the radical. That's it. So for example, if I gave you, I don't know, square root of -21, what do we write first? I. What goes in the radical? 21. That's it. That's all you need to know about the I's. Okay? See a negative inside. You no longer get to say not a real number. You now say, oh, that's just something with I. Okay, so that means that we can finish this problem that we had left off with over here. I think I need a little more space. I'm going to write it over this way. 4 plus or minus square root of -4/2. This is where we were. And we have just discovered 4 plus or minus that the square root of -4 was really what? I times 2, right? I'll write it with the 2 first. Okay, that's what we found. And then just like we simplified our quadratic formula answers last class, we're going to do the same thing here. We're going to split this into 2 fractions. What's the first fraction? 4/2. And the second fraction? 2I/2, right? That denominator goes for both fractions, and then you split the numerators. And then you can reduce these fractions separately. 4/2, that's 2, plus or minus. 2's cancel here, I. There's our answer, 2 plus or minus I. And I want to be clear, even if this is the first time you're seeing I, it's like it, it might sort of be alarming to have a letter in the middle of your math answer, your numerical answer, but we're doing something real here. If you take 2 plus I and you substitute it right here for that X and that X, if you make them both 2 plus I, and you do lots of distributing and lots of combining, you will get 0 at the end of the day. You are finding a number that makes this equation true. It just happens that number has an I in it, but it's no less legitimate than any of the other solutions to equations we found. Okay, so I think that's it there. Let's move on to the next page. And we're going to take a look at these 4 different parabolas here. So first question. How many x-intercepts? We're going to focus on x-intercepts for each of these 4 parabolas. How many x-intercepts does this graph A have? 2. Graph B? 1. Graph C? 2. Graph D? 0. Right? Those are the only possibilities for a parabola. It's either got 2 or 1 or 2 or none. And the 2's are there twice because they're different kinds of numbers. Let's review these words right here. Rational number and irrational number. Most of the numbers we've been playing around with this semester have been rational numbers. Any rational number can be written as the ratio of 2 integers. That word ratio is why we call them rational. Right? Ratio right in the beginning of that word. So anytime you write the ratio of 2 integers, you are writing a rational number. So for example, half or 256 or -73/10. Anytime you have 2 integers in a ratio, it is a rational number. But if you have a number with a radical in it, square root of 10, for example, it is called irrational. It is not possible to write the square root of 10 as a ratio of 2 integers. And so let's take a look. So largely, the rational numbers are the ones that we think of as being nice numbers, and the irrational ones are not as nice. Taking a look over here again at the x-intercepts, it sure looks like it's -6 and 1. Are those rational or irrational? Those are rational. take a look at the single x-intercept. What's your guess for this number? It looks like it's 2. Is that rational or irrational? Rational. Okay, then it gets tougher down here because now I can't tell what the numbers are, right? Like I think we guessed at this one last class. We said like 1.4. I'm looking here. We said that was around 1.4 and that was around negative 3.4. And then we used the quadratic formula and we got like our actual answers. And our actual answers had square roots in them. Rational or irrational. If it's got a square root in it, it is irrational. So these are 2 irrational numbers. And as we said over here, there's no x-intercepts. But my goodness, every time I solve a quadratic equation, I'm going to get 2 answers. And what did we discover? What kind of answers did we get when we used the quadratic formula here? We didn't get real numbers. We got imaginary numbers. 2 imaginary solutions. Okay? So it turns out these are the 4 possibilities for any parabola, any quadratic that I give you. It either has 2 rational solutions, 1 rational solution, 2 irrational solutions, or 2 complex solutions. There are no other possibilities. There's other ways to mix and match those words. You could say like 1 irrational. That's not one of the things that's up there, and it turns out it is just simply not possible. No way for a parabola to have 1 irrational x-intercept. You could look for like 1 imaginary solution. Not going to happen. Never, ever, ever. Okay, so the question is there a shortcut to know how many and what kind of solutions we have? And that's the meaning of this word nature. The nature for this particular graph is 2 rationals. For this other one is 1 rational. It's how many and what kind. So here is a shortcut for figuring out how many and what kind. First, we got to define something. It is this word here, discriminant. If you have a quadratic equation, standard form equals 0, the discriminant is this expression, b squared minus 4ac. Where have we seen that particular expression before? It's in the quadratic formula where? Under the radical, right? That is exactly the thing inside the square root in the quadratic formula. Okay, so what? Let's see if we can do some calculations here. Here are the equations for the 4 parabolas. They're all y equals parabolas, but these are 0 equals for our equations. Let's go ahead and calculate discriminant here. 0 equals x squared plus 5x minus 6. b squared minus 4ac. Something squared minus 4 times something times something. That's what we're computing here. How much is b for this first parabola? 5. So that goes there. How much is a? 1, and c? Negative 6. Good. And make sure we grab that negative. Okay, so we will do arithmetic here. 25. Ultimately, is this a subtract or an add? That's an add, 2 negatives. That's a plus. 4 times 1 times 6, 24. Altogether, 49. 49 is the value of that discriminant. So defining the discriminant serves no purpose unless we can do something with it, and I'll show you what we're going to do with it after we finish filling in this table. Okay, so let's calculate 3 other discriminants. We'll do these ones just a little bit quicker. B squared, that is negative 4 squared, minus 4 times 1 times 4. B squared minus 4ac. That is positive 16. Subtract 16. That discriminant is 0. Moving on to C. 2 squared minus 4 times 1 times negative 5. 4 plus 20 is 24. And in the last row, negative 4 squared minus 4 times 1 times 5. This is the one we did earlier today. 16 minus 20 is still negative 4. Okay, and then we're going to fill in this last column here, which is the nature of the solutions. We're just copying the answers that are below each of the graphs. So the graph A in the top left, right below the graph, it says 2 rational solutions. What did it say for part B? 1 rational solution. What did it say for C? 2 irrational. And then finally D. 2 complex. Okay, and so what we're going to do right now is connect the numbers in that third column to the words in the fourth column. Right? There's a relationship. And in fact, there's a theorem that we're about to discover. If you just tell us what the number is, what the discriminant is, we immediately know which of these 4 possibilities is the answer. And again, those are all 4 possibilities for any quadratic, not just these 4 particular quadratics. Okay, let us think about that discriminant. Remember, the discriminant is the thing that is inside the square root, right? B squared minus 4ac goes in that blank. In the first case, the discriminant is 49. What is the square root of 49? 7. And so it doesn't really matter to me what negative b and 2a are, but this thing right here is going to be rational. Agree? Because that square root of 49 just became plain old 7. And so ultimately, this is just an integer on top and an integer on the bottom. And so the solutions here are going to be rational because that square root just plain disappeared. And how many are there? Well, it's plus or minus. There's 2, right? 1 for the plus, 1 for the minus. So what was special about 49 that gave us the conclusion 2 rational solutions? 49 was what kind of a number? It's positive, and it was a perfect square, right? That's what made this thing get rid of the radical. So anytime you have a positive number for your discriminant and it's a perfect square, the conclusion is 2 rational solutions. Okay, let's change this 49 to the next row. The next row, the number was 0. What is the square root of 0? 0. Square root of 0 is 0. Okay, so then I'm going to get negative b plus or minus 0 divided by 2a. Okay, is that going to be rational or irrational? It's rational. The square root disappears. And how many are there? Well, I said plus or minus gives you 2, 1 plus and 1 minus, except if, I'm just going to make up numbers there. Let's suppose it's negative 5 plus or minus 0 divided by, I don't know, 8. If you do negative 5 plus 0, what do you get? Negative 5. If you do negative 5 minus 0, what do you get? Negative 5. So adding or subtracting 0 makes absolutely no difference. How many answers are there? There's 1. Normally there's 2. When you add and subtract, you get 2 different things, except in this one case with the number 0 popping out. 0 is the only number you can add and subtract, and you get exactly the same thing. So if you get 0, only 0, you're going to get 1 solution, and it's going to be rational every single time. That's our conclusion. Let's go to the third row. In this case, the discriminant was 24. The square root of 24 is an irrational number. So the final answer to this thing is going to be an irrational number. And how many answers will you get? There is a plus and there is a minus. How many answers is that? 2. So you're going to get 2 answers and they're going to be irrational. What was it about the number 24 that made it so we were irrational? It is not a perfect square. That's the difference between the 49 and the 24, right? Square root of 49 became just plain 7. Square root of 24 is an irrational number. So that's the distinction. Perfect square to rational. Not a perfect square to irrational, okay? And then finally, the last one is pretty easy. I will put in my square root here, negative 4. What kind of a number is the square root of negative 4? It's an imaginary number, or we can call it a complex number. It is not rational, it is not irrational. It is a completely separate category of number. So here, it doesn't matter about the 4. Instantly, if you see a negative in there, your conclusion is always two complex numbers. 2 because of plus or minus, and complex because it's the square root of a negative, okay? So all of that is concluded on the very next page. If you're equal to 0, 1 rational. If you are less than 0, 2 complex. If you are greater than 0, well, that's these last two cases. You have to ask a further question if your discriminant is bigger than 0. You have to decide whether it's a perfect square or not. If it is a perfect square, 2 rationals. If it is not a perfect square, 2 irrationals. Those are all 4 possibilities. Any case for the discriminant, you can handle it by finding which of these 4 it is. So the activities on the next page, we're going to change it up a little bit. Let's do number 1 together, or at least let's start number 1 together. So here are the instructions. First, you're going to find the discriminant. That's going to be a number. Then you're going to write the nature. That is some words from that last column from the previous page. And then you're going to go on and find the full-fledged solutions. So let's do the discriminant first. B squared minus 4ac. How much is B? 5. A. 2. C. Negative 2. Okay, let's crunch the numbers. 25. Is this an add or subtract? That's an add. 4 times 2 times 2, that's 16. 41. Flip back to the previous page for just a second. There are 4 cases there, A, B, C, and D. 41 fits into exactly one of those cases. Pause for one moment and figure out which case is the magic number 41. B squared minus 4ac, in this case, is the 41. A, B, C, or D, which one is this? 1 vote for C. Any other votes? 1 vote for D. Other votes? For sure it's not A or B, right? A is 0, B is negative. It's not, it's 41. So if it's positive, you ask the other follow-up question, perfect square or not a perfect square. What do you say about 41? Not a perfect square, which makes that case, which one? D. And the conclusion for D is to what? Be irrational. That's all you write. The nature of these solutions, there are 2 irrational solutions. Okay, and then we'll finish. We'll go a little bit farther here. Discriminant is just a shortcut to tell you what kinds of answers to expect, but here I actually still want you to find the answers. So in this case, we're doing our full-fledged quadratic formula. So in the beginning here is negative b. What am I writing here? Negative what? Negative, try again. Negative 5, right? B is that 5 there. Plus or minus, leave the square root blank for just a second. And on the bottom here, we're supposed to do 2a. 2 times what number? 2a is 2 times 2. Okay, in the blank, in that square root, we're supposed to put b squared minus 4ac. Do not start over with that calculation. We've already done it. How much is b squared minus 4ac? It's 41. We just put it there. Okay. Don't do it again. You've done it already. And so our answers to this one, negative 5 plus or minus square root of 41, all divided by 4. That's all. Okay, I guess technically we've been splitting this into 2 fractions, and then we try to reduce the square root of 41. Turns out we can't reduce 41, it's a prime number. And so that's our answer there, or you could split in 2 fractions. That's it, okay? So don't write either of those for this guy. If you're describing the number 41, you would describe it with the word prime. Numbers are prime, expressions are irreducible, but we don't actually need to write that. Okay. All right. So go ahead and move on with this activity, starting with number 2. You got some work to do with number 2 before you even begin the discriminant. It does not look like it's in standard form just yet. So take your time there. We'll walk around.